So, welcome to the 25th lecture of surface engineering. At the moment we are discussing in the last couple of lectures about various approaches possible for hardening the surface primarily of steel. We started discussion with various mechanical deformation aided processes like shot pinning or shock pinning or laser shock pinning, wherein the entire process was only based on certain deformation or plastic zone induced onto the surface. Then we talked about flame or induction hardening, where we used thermal activation, heating through one of the two, either of the two possible ways of heating, flame or induction. In both the cases, one thing was in common, though one was mechanical, the other one was thermal process, but one thing was common. The surface chemistry we did not change. So, essentially they were surface hardening processes without changing the composition of the surface. Now, we are going to discuss another set of surface hardening exercises, which essentially is not just, which is certainly not mechanical, which is thermal, but to be more precise, which is thermochemical in nature for obtaining the desired aim. So, this process is called carburizing, and herein we actually, if you recall in the previous lecture, we said the steel that we generally use should have a minimum content of about 0.4% carbon, 0.3 to 0.6 or 0.8, typically more than 0.4 weight % carbon in the steel, because we don't change the chemistry, and that's the minimum amount of carbon we need to be able to convert the surface into martensite, and that martensite should develop adequate strength or hardness, and in order to get that you require a minimum amount of 0.4% carbon. Compared to that, if you now look at this carburizing process, as I said, this is a thermochemical process. So, here again, if you refer to the steel part of the phase diagram, iron cementite diagram, then this is the eutectoid point. Usually this kind of treatment is applied to mild steel, low carbon steel. So, now we are talking about a range which typically would be about 0.1 to at the most 0.3 weight % carbon. So, purposely we are choosing a stock which has lower carbon, so that the component that we are going to treat will actually have a core which will be not only ferritic or ferritopearlitic, but because of low carbon will actually be much more softer and eventually provide higher toughness for the entire component. So, this portion we purposely want to remain as soft, and that is why we require a carbon content which should be sort of in this range. But in order to get requisite hardness or optimal hardness of martensite at the surface, we already know that you require carbon content which is certainly more than 0.4% carbon. So, now we need to enrich the surface with carbon. The process of carburizing essentially is a technique by which we can enrich the surface with carbon by solid state diffusion. So, we do not take the stock to temperature above melting temperature, it is entirely a solid state process. Now, we again need to go to a temperature which has to be higher than the AC3 temperature. Why is it so? Because we want the entire microstructure of the steel to be austenite. And why austenite? Because austenite, we all know, is FCC, face centered cubic structure, and the maximum carbon solubility or the limit of carbon solubility in austenite is much higher, is highest in all the possible solid phases of steel, and that would be typically, if I draw it afresh, then this is the steel portion we are talking about, and this is the eutectic isotherm beginning. So, this is the portion which is approximately 2% carbon. So you can pack in as high as up to 2% of carbon in the interstitials of austenite, not in ferrite. In ferrite, the maximum solubility is only 0.025%, and that too at the eutectoid temperature. At room temperature, of course, we have nearly zero. At room temperature phase is ferrite, and ferrite typically the room temperature solubility will be very, very low, typically let us say 0.0078%. So, in order to pack maximum possible amount of carbon, we need to go to austenite, and we cannot afford to do that exercise in the ferritic zone. So, that is why first of all we choose low carbon stock, so that the core remains inherently soft and eventually provide the required toughness, but on the other hand the surface should be enriched in carbon, and for that reason the surface we want up to a certain depth to go to austenitic range, so that during diffusion, solid state diffusion, it can acquire carbon which can be, usually we target somewhere in this range up to about, say, somewhere around 0.4 to maybe 8, maybe up to about 1% carbon. So, typically in this range, but one can go theoretically to as high as 2% carbon. So, the process is the same, as I said, enriching the surface with carbon. We heat and then take the surface up to a controlled depth to austenite, and then subsequently we employ a separate heat treatment to convert the carbon enriched surface to go to austenitic range and then subsequently be quenched to martensite. What we get in turn is a strong, wear resistant surface, and the stock to begin with will be ideally a low carbon steel, which is used for various manufacturing processes. Now, when you do carburizing, then with time actually how the depth of carbon penetration changes. So, this is A is up to 6 hours and B is up to 12 hours. So, by employing another 6 more hours, you can increase the depth of carbon penetration typically from about let us say 300-400 micrometer to almost close to a millimeter. So, the carbon penetration from the surface, so if this is percentage carbon and if this is depth Z, so this is the surface and this is towards the interior, the carbon diffusion profile will be like this. So, up to a certain depth, our idea is that if this is the desired depth, so within this desired depth region, one should have at least the minimum amount of carbon. So, this cutoff point is typically about 0.4% carbon, and this is the depth from the surface which would have acquired the required amount of carbon, which can be more than 0.4% carbon. So, as I said, this is a thermochemical process, diffusion controlled. We start with a low carbon steel, and which may have other alloying elements, but we actually produce carbon penetration up to a certain depth, which can be a millimeter or certainly less than 1 or 2 millimeters. But if needed, we can go even up to 6 millimeter. So, the effective case depth can be as high as 6 millimeter. So, in order to introduce carbon to the surface, we need carbon containing or carbonaceous environment and expose the material to somewhere around 880 to 1000 degrees centigrade, because that is the temperature range where everything is austenite and solubility of carbon in austenitic stage is higher. All carburizing treatment is to be followed up with a separate heat treatment called quenching process, but an even tempering process, but that we will discuss some other time. So, what is important for us is to know that we are exposing to a fairly high temperature, above 900 or so, and hold for a certain period of time. So, both temperature of heating and the time of holding, both are very important, because the whole thing is diffusion controlled, and we know diffusivity is a function of both temperature and not time, but the diffusivity is a function of temperature, but time also for a given at a given temperature, time and temperature overall will determine what is the depth of carbon penetration. So, if this is the surface after carburizing and this is towards the core, so this kind of a gradation of microstructure we see. So, typically this is where we have much larger carbon, this is where we have carbon content which is in between, and this is where the carbon content reduces, and we actually can get I'm sorry, I'm sorry, I made a mistake here. This is the core region and this is the surface region. So, this is the so-called hyper-eutectoid zone and this is the hypo-eutectoid zone, low carbon. So, what you are seeing, these bright regions are the ferritic regions and these are pearlitic regions. So, this is a ferritopearlitic core, which is what we had at the beginning, and this is the mixture of ferrite and this is the mixture of this is the region where you have introduced more amount of carbon. So, the volume fraction of area fractions of ferrite pearlite is changing, and so let us say typically this would be in the range of, if this is 0.2% carbon, this would be typically about 0.4% carbon, and this may be more than 0.6% carbon, and this certainly is the hyper-eutectoid range. So, obviously, you are talking about a carbon range which is greater than 0.8% carbon. So, we create compositional gradation and hence microstructural gradation after carburizing treatment. This is a vacuum carburizing furnace typically used for carburizing, but gas carburizing, not the pack carburizing that we are talking about. And these are the typical components which are used for which are subjected to such carburizing treatments. So, it can be a long shaft, a camshaft, or gear wheel, or a ball bearing assembly, and so on and so forth. So, the carbon profile and the penetration depth, they will depend upon the time of exposure, the carbon activity in the environment, which can be solid or solid converted into gas, and the temperature that we employ. Of course, the base composition of the steel is also important. So, we need to expose for a certain period of time to build the required amount of carbon potential and at a thermal temperature that we subject the stock to. This process, as I said, is based upon creating a carbon rich environment, and that will primarily depend upon the ratio of carbon monoxide to carbon dioxide. So, this gas mixture ratio determines what is the carbon activity in the furnace, which is what is going to dictate what would be the depth of penetration of carbon into the surface. Typical applications, as I already mentioned, could be on the bearing assembly, the gears, the cutting heads, the shear blades, even shafts or cams, and so on and so forth. But these are all, to begin with, they should have very low carbon, so mild steel 0.2 or so, and the case depth can be to the maximum something like about 5-6 millimeter. We will come back to this discussion of this diagram later, because in this discourse we are only talking about the carburizing and not the subsequent heat treatment. Once you have completed the heat treatment, typically, but even after carburizing treatment, this would be the carbon diffusion profile, and eventually this is the kind of a hardness profile that you can generate, and because of the Martensich transformation, you can also create residual compressive stress up to a certain depth below the surface. So, this would be the range from the surface which will be developing residual compressive stress. But remember, this kind of profile you can generate after the heat treatment that follows up carburizing treatment. So, this is the cross section of the tooth of a gear, and this explains exactly what we are trying to do by way of this carburizing. Please remember, in case of induction hardening or flame hardening, you would have also got a very similar cross-sectional profile, but the difference was that there the steel, the stock that we subjected to must have had already adequate amount of carbon. So, the initial composition of the steel must be already having more than 0.4% carbon. But here we are dealing with a material which is having in the core to begin with only about 0.2% carbon. But the surface that we develop, this bright region, white region that you are seeing as the contour line, this bright region is highly carbon enriched, and it can be actually close to eutectoid or even hyper-eutectoid. So, we see a compositional gradient from the surface towards the interior, and this gradient gives you predominantly martensitic, martensite plus pearlite, and then subsequently ferritopearlitic microstructure. So, that is kind of a desired scenario that we want to develop through this case hardening process. What we actually want to achieve is to not to sacrifice ductility. We want to retain ductility, we want to retain toughness, but we want to increase the hardness and strength of the surface. So, this is a tall order to have this kind of a combination. How do we do it? So, in some cases this is called pack carburizing or even box carburizing, because you actually take a cast iron box like this, then this is your component and this is your component, and you pack it with solid substances which are essentially graphite and then calcium carbonate or barium carbonate or some other activators, and we may have also certain other oxides. So, what is most important is this activated charcoal. This is the main source of carbon, but please remember that if you use it, we will come to that in the next very slides, but let me just tell you that we need to seal up these portions here, because we do not want fresh entry of air into it, and we expose this whole thing inside the furnace. So, it goes inside the furnace, and then we heat up to an isothermal condition, which could be, as I said, anything from about close to 800 to 1000 degree, depending on what the initial temperature, initial carbon content of the steel is. So, in pack carburizing, what is important, again let me repeat, is that we are beginning with low carbon stock. This is the kind of arrangement that this is the box which is packed with this particular, let us say, shaft, and packed with these carbonaceous materials, and the typical reaction which is responsible for carbon diffusion is like this, where carbon reacts with carbon monoxide and deposits in the process in the cooler region carbon onto the surface, but the difference is that this carbon is so called activated carbon. So, this activated state is very important for carbon to diffuse in, and schematically, if this is carbon enriched region, then this is how the carbon atoms are able to penetrate to the surface and actually diffuse farther down and reach up to a certain depth. So, they are not substituting an existing alpha iron atom, but they are going into the interstices. But when one interstitial position is occupied, it immediately creates a fair amount of strain fill around, so that the subsequent spots are not necessarily filled up immediately. On the other hand, depending upon the time that you allow, this time essentially determines to what depth you actually can expect carbon to diffuse in. We also have seen that the carbon diffusion profile decays with depth. So, as we go lower and lower, the carbon content decreases. Obviously, surface which is exposed to the carbon rich environment will actually have the maximum amount of carbon, and the way below down inside you will have the least amount of carbon. So, this is how the carbon profile changes or decreases, and we have already discussed that the typical case depth could be a few millimeter, maximum 6 millimeter, and the cutoff point here should be 0.4% carbon. Now, what is a reaction that actually takes place inside? It's not the charcoal which is the one which actually starts the process. It's actually this activator, barium carbonate, which dissociates at 900 or 800 degrees centigrade and dissociates into barium oxide and carbon dioxide. Carbon dioxide now reacts with activated charcoal or graphite and converts this carbon dioxide into carbon monoxide. Carbon monoxide, when it comes in contact with steel or iron at high temperature, then it actually decomposes and dissociates to deposit activated carbon, so atomic carbon. Now, this is very important, that this is in an activated state, not in a molecular state, because unless it is in an activated state, it cannot easily get adsorbed and subsequently absorbed by diffusion. So, what is important is that the carbon at the surface is initially goes through initially gets adsorbed and then finally get absorbed by diffusion. So, we must have sufficient solubility for absorption, and this is why exactly we always go to the austenitic range and then don't do it in the ferritic range. We already learned that austenite can actually dissolve as much as up to 2 weight% of carbon. The temperature range would be, that varies depending upon the stock that you are dealing with, its initial composition and the depth to which you want to go and so on and so forth. And then, so this is important here, that the so-called case depth that we are talking about will be a function of time and temperature. So, at a given isothermal temperature, the diffusion coefficient, as we all know, is a function of, is proportional to the temperature. So, this is the factor which determines what is the effective diffusion coefficient, and once we know the, so this K basically is proportional to diffusion coefficient, and for a given temperature, since the D is fixed for a given temperature, so what we now need is to determine what should be the possible depth, and this possible depth is actually proportional to the square of the temperature, because it is derived from the relationship which is somewhat like this. So, D is constant, then obviously the depth, case depth essentially depends upon the square of time. So, higher the time, higher will be the depth of penetration. But I would like to re-emphasize the fact that in order to enrich the surface with so high carbon and achieve a depth up to about 1.5, 2, 3, maximum 6 millimeter, we should have sufficient carbon potential in the environment, and that is possible through this kind of a reaction, where barium carbonate dissociates, gives barium oxide and carbon dioxide. Carbon dioxide reacts with activated charcoal, creates carbon monoxide. Carbon monoxide, when it comes in contact with the hot surface of steel, it dissociates and deposits activated carbon, and this activated carbon now gets adsorbed and then subsequently absorbed into the stock by way of diffusion. And the depth of diffusion will be determined by the time, the square root of time at a given isothermal temperature, and diffusion will be dictated by the so-called diffusion coefficient at that particular temperature. So, now it is time to recapitulate what all we have discussed. So, as I said right in the beginning, compared to shot peening or shock peening or laser peening and so on, this is different process where we are taking not only the help of heating or thermal effect, but also we are changing the chemistry. So, this is a thermochemical process compared to the other processes that we have discussed. Then this whole technique is aimed at enriching the surface with carbon, and we just heard that how do we do that? We actually take charcoal, we take barium carbonate, we dissociate, certain reactions take place in the vapor state, and eventually carbon gets deposited in the activated form, and that activated carbon diffuses inside. The diffusion profile is actually decaying from the surface, highest at the surface, and then gradually decreases. The typical process parameters, of course, would be the activity of carbon that we create, the temperature, the time, the surface condition, and of course the initial carbon content of the steel. There's one important point that I need to address here. If we basically can divide the entire range of steel for all engineering applications into two main parts, the so-called hypoeutectoid and hypereutectoid. So again, if you refer to the steel part of the diagram, then so below the eutectoid point, everything is called hypoeutectoid, and above the eutectoid point in terms of composition is called hypereutectoid. So if we are dealing with hypoeutectoid, then this is the temperature band we target to achieve. While treating hypereutectoid steel, we don't necessarily go above the ACM. Here we go above AC3, but for hypereutectoid, we don't go above ACM. That's purely because the temperature here is fairly high, but already if the steel, let's say, is 1.2% carbon or 1.1% carbon, generally these kind of steels are never subjected to carburizing treatment, but for whatever reason, if you are doing anything with hypereutectoid, you would rather heat only above the eutectoid and not necessarily go above ACM, because above ACM you first have to go to very high temperature. There could be subsequent large thermal shock or thermal distortion during quenching. More importantly, because of exposure to much higher temperature, you actually can undergo undesirable amount of oxidation at high temperature. But the most important thing is that when you go above the eutectoid temperature for hypereutectoid steel, you already have 90% of the volume converted into austenite. If you apply lever rule for 1.2% carbon steel, you can easily see about 80 to 90% of the microstructure is already austenite, and the remaining part will be cementite. Cementite is a hard phase. So even if you retain 10-20% of cementite in the microstructure, it's not going to do harm. Rather, it's going to provide you more hardness, or more, it's going to make the whole microstructure stronger. But your main intention is to convert austenite into martensite. And if you already have 80% of the microstructure in austenitic state, even though you have heated only just above AC1 and not above ACM, you better as well stay at that temperature range and be happy with 80-90% of austenite, instead of trying to go all the way up above ACM and incur the disadvantages of spending more fuel, spending more money on heating, exposing to more oxidative situation, and also incur a greater amount of thermal shock while quenching. So, and the time that we require for soaking will be primarily dictated by the diffusion coefficient, and hence the temperature that we are referring to. So that determines what amount of time we need for carburizing. So that's all for the time being. Thank you very much.